I'll get started. So the swag for today is about League of Legends, and again, lots of this could be applied to many different possible games. It isn't just this one game, but in this particular game, your attacks do damage to enemy champions, and you can purchase various items that will either increase how quickly you can attack, or the damage that your attack does, or various other effects. And some attacks will have a crit chance, which is the chance of a critical strike, which is going to cause double the damage, which is pretty awesome. And just to start off a basic situation, imagine without any modifiers, your attack does 100 damage and it has a 1% crit chance. And you can attack once per second. So pretty basic set of assumptions. What we can do is define a variable, a pretty simple looking random variable, to measure the total damage you can do in 15 seconds. And see if we can find the mean and variance of that total. Well, we'll start by defining, let's call it W to be the damage on one single attack. And again, it's kind of, this is a weird little loopy thing, there we go. 100 with probability 99% and 200 with 1% chance, because that crit chance is going to double your damage. So again, it's not a very complicated random variable. It only takes two values, and so it's clearly discrete because 2 is countable, and with those corresponding probabilities. So then by definition, we take the expected value of this random variable. Expected value of any random variable is the sum over all values of the random variable of the value times the probability that it takes that value. So it's like, this is for W here, it could be X in general, the sum over all W of W times F of W. That's the expected value of W. If it's X, that's the sum over all X of X F of X. That's what we get here for our expected value. So in this case, there's two possible values, 100 and 200, and then we're multiplying by the probability, 0.99 and 0.01. And altogether we get a mean of 101 damage per attack, and in 15 seconds you can do 15 attacks. And so another cool thing about expectation is that it's linear. So the expected value of W plus W plus W plus W 15 times added up, you can just break that up into the expected value of W plus the expected value of W plus the expected value of W added up 15 times. So because of linearity, the total expected value of the number of attacks that the total damage that you do in 15 seconds is going to be 15 times the damage that you do in one attack. So that gives us 15. Then for the variance, again, if this is new to you, okay, sorry about that. The variance of a random variable, by definition, is the expected value of a function of that random variable, which is W minus E of W squared, and then close the bracket. So notice that the squaring is happening inside of the square brackets. So unfortunately, while I mentioned expectation is a linear operator, this is not a linear function of W. So we can't just pull the thing outside. This is not equal to the expected value of W squared. Like you can't just move the square to the outside because it's not a linear function. But what we can do is expand this square and then rearrange, and we end up with the following. We get E of W squared minus E of W squared. And again, notice the first squaring is happening on the inside, the second one is happening on the outside. And those are different things because W squared is not a linear function of the random variable, and so this is not going to be 0. And again, what variance measures is the spread of the distribution. A larger variance is going to have a wider spread of the distribution. A smaller variance is going to be always very, very close to the mean. If you want to think about it, what variance is doing is calculating essentially the average squared distance from the mean. That's what it's doing. So the further you are from the mean, that distance gets squared and then multiplied by the probability that you are that far away, and then added up over all possible values you can take on. But usually the way we calculate variance is this second method here. So let's do that for this case. The expected value of W squared, we're going to take 100 squared times 0.99, right? Because we're squaring each value of the random variable. And then 200 squared times 0.01, which is 10,300. And then we can use this formula here to take the variance of W as that, 10,300, minus the mean of W squared. So minus 101 squared, that ends up giving us 99. So that's the variance of a single attack, but we want the total variance of 15 independent attacks. So the variance of one attack plus the variance of another attack plus the variance of another attack, etc., added up 15 times. And that gives us a total variance of 1485. But variance is actually measured in units squared. So like if damage is measured in points or whatever, then variance is measured in points squared, which doesn't always have an interpretation. So you often would take the square root of the variance. So the standard deviation of any random variable is just the square root of the variance. And that's going to be measured in the same units as the random variable. So that's just a little bit easier to interpret. So 38.5 is measured in points, like damage points. That's the standard deviation of how much damage you can do in this situation with your basic attack. All right, so that's kind of the big bare bones version of mean and variance. If you haven't watched any of the week 6 videos, you probably should do that, but that gives you just an idea of what mean and variance are. But now we can imagine that we're going to modify this attack, right? Like this was our basic attack without any modifiers or any particular like items or anything. So imagine you have a choice between 3 of these items. We have the Brawler's Gloves, which gives you 8% higher crit chance. We have a longsword, which gives you more damage, so plus 10 attack damage. Or we have a dagger, which you can use faster. So you do the same attack, but you actually do more attacks per second. So we want to think about what impact are these changes going to have on the total damage you can do in 15 seconds. So we can investigate each one of these items and recalculate the mean and variance of the amount of damage we can do in that time and see what we get. It might be interesting. So let's see. We'll just one at a time. A lot of this is fairly repetitive, so I'm not going to go through everything exactly. With the Brawler's Gloves, the values are the same, 100 and 200, but what's changed is our crit chance here. We have 91% to equal 100 and 9% to equal 200. So when we calculate the expected value, it's going to be quite a bit higher because we have a higher chance of doing that double attack, and then we end up with an expected value of 1635. For the variance, again, we use the same procedure. We calculate e of x squared, and then that gives us a variance of a single attack of 2499. And then the variance of 15 independent attacks is 37,485, or a standard deviation, that's what we kind of like to look at, of 193.6. So you can see here, the mean is higher, which makes sense. The standard deviation is huge, like a much, much bigger standard deviation because we have more of that crit chance. What about the longsword? Let's see what happens here. We're just going to do, again, same thing. We're doing plus 10 attack damage, which means our normal attack does 110 damage, and our critical hit does 220 because it's doubled. So the probabilities are the same as before. So similarly, we can calculate the expected value of y. We get 1666.5, so actually pretty close, not like maybe it's actually a little bit higher than with the Brawler's Gloves. And for the variance, again, same calculation as before, but we end up with a standard deviation of 184.2 over the 15 independent attacks. And then finally, what about the dagger? So actually, the attack damage on a single attack is the same. So it's the same as W because we haven't actually changed how much damage each attack does. We've just changed how many attacks we can do in 15 seconds. So the mean and variance of a single attack is the same, but we can now do 17 attacks within 15 seconds. And so the expected value is going to be 1717, that's 101 times 17 instead of 101 times 15. And the variance, similarly to before, it's going to be the same variance that it was, added up 17 times instead of adding it up 15 times. And that's a standard deviation of only 41.0. So this is pretty cool. We can kind of look at all of these ideas, and we see that the 3 means with these 3 new attacks, sorry, I'm covering up some of them here. We've got 1635, 1666, and 1717. So they're all relatively close together. But the variances are very different. There's a lot more variability with the Brawler's Gloves and the Longsword compared to Dagger, which lets you do basically the same thing, just more of it. So we end up with this comparison between the higher risk, basically, of those higher variance strategies that might have a possibility of a bigger reward. As well, of course, this was just a very simple example with items that just increase one thing. There's, of course, items that increase different things in combination with each other, so you could have all sorts of different things stacked on top of each other, different bonuses. But you could always do this sort of calculation. Just think about what will these things do to your chance or the amount of damage that you'll do, and then you can calculate that. And actually, there'll be a question kind of like this, spoiler alert, on your next computer-assisted assignment. As well, of course, like here we weren't considered with the cost of these items, but items have a cost. So you could factor that into your decision-making to find the optimal way to spend your money within the game. All right, so that is it for the first part of the swag, but I actually have a second thing to say about League of Legends. Yeah, I think I'll go into it. So that was, again, using your items and how they can affect the damage that you can do is a really nice, quick application of mean and variance. The other way that we could do is how to figure out, like, how to progress through the leagues, or through the tiers in the game. So how it works, again, if you've never played, no worries, but lots of other games have similar ideas like this. So you start in Bronze 5, which is Bronze Tier Division 5, and once you get 100 points, and it's based on sort of the ELO system, then once you get up to 100 points, you can sort of like try to get promoted to the next division. So you have like a 2 out of 3 game that you have to win, and then if you win the 2 out of those 3, best 2 out of 3, then you get promoted to Bronze 4. And then that continues to get to Bronze 3, and then Bronze 2, and then Bronze 1. And then from Bronze 1 to go up to Silver, you need to win a best 3 out of 5 promotional games to go from the Bronze tier to the Silver tier. And then similarly, within Silver, you go to Silver 5, then within that you go to Silver 4, 3, 2, 1, and then Gold 5, 4, 3, 2, 1, Platinum 5, 4, 3, 2, 1, Diamond 5, 4, 3, 2, 1. So it takes a while to get all the way up, but I'm curious, how long does it actually take? Like, how many games on average, and what might be the variance around that? So let's think about that. In order to investigate this at all, we sort of have to note how the ranking system works. And essentially it's just a modification of the ELO system, which is used for chess players, and it's actually also used on Board Game Arena. If you've ever played on Board Game Arena, they use the ELO system for that. So basically, it kind of like, if you beat somebody that you're worse, like that your score is lower than theirs, you earn more points. If you beat somebody that you're much better than, you don't earn as many points. And if you lose to someone who's much worse than you, then you lose a lot of points. So it's kind of like, basically, where do they think you should be within the ranking? And every time you play a game, your ELO score goes up or down accordingly. It's not exactly the same in League, but it's kind of similar. So you have a matchmaking ranking, and it goes up or down based on these factors. And imagine we're just sort of like, you're relatively well matched, so your MMR and your skill increase proportionally to the opponents that you're playing against. And then if that's true, then on average you'd probably win about half your games. And you would sort of gain points, like league points, consistently for wins and lose them for losses. Of course, again, we know that's not actually true, but we're just making some simplifying assumptions here. So if we do that, we're going to start at the bottom. You have no league points, and every time you win a game, it goes up. Again, we need to make an assumption. Let's assume it's a uniform amount between 1 and 25. But if you lose, it goes down between -1 and -25. And you only get demoted, like, if you lose a whole bunch of games in a row while you're at 0, so we're just going to assume that's not a possibility. It is, but it has a very small probability. So we're going to just hope that you're motivated enough not to get demoted out of your league. So if you have a 50% chance of winning each game, then the expected amount of league points you gain on each game is, basically, we're using the law of total probability here, kind of, like the probability that you win times the expected LP if you win, plus the probability that you lose times the expected LP if you lose. And if the LP that if you win is a discrete uniform random variable on 1 and 25, then the expected value of your LP on a win is going to be equal to, well, 1 plus 2 plus 3 plus 4, blah, 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 up to plus 25, divided by the number of possible values there are. Because a uniform random variable, discrete uniform, has probability of equaling each value the same for every value. And if there's 25 different values, then that probability is 1 over 25. So basically we end up with 1 plus 2 plus 3, etc., up to 25, all divided by 25. And that is 13. You can double check that if you like. But it kind of makes sense, right? If it's uniformly distributed between 1 and 25, then on average, it's going to be right in the middle. That's true with a uniform random variable. And then actually same thing. If you lose, right, it's between -1 and -25. So on average, you're going to have -13 points. So when we put that all together, we have, again, 0.5 times the number you gain on average if you win, plus 0.5 times the number you gain on average if you lose, which is -13 gain. That's equal to 0. So that's no fun, because that's kind of annoying. Like, what if it makes sense though, like if you are in the exact right place for yourself, where you're equally matched skill-wise with all of your opponents, then on average, you're expected to stay there. And that makes sense, but it's like, no, I want to get better. So let's imagine instead that you actually are slightly below where you belong skill-wise. So you're actually more likely to win than your opponents, and you keep improving. So as you go up, you're always 60% likely to win. So you're just a little bit better than all the opponents that you're playing, even as you progress through the leagues. That's always nice to think you're just a little bit better than the people that you're playing against. So in that case, we can redo this very same calculation with a 0.6 and a 0.4. And now that means on average, we're gaining 2.6 league points per game. Okay, well that means if we want to gain 100 league points to get up to be eligible for a promotion, that would take on average 38.46 games. Just simple dividing 100 by 2.6. And again, that's assuming that we don't get demoted, which has a small probability of happening. Okay, so that's cool. We play 38.46, so maybe 39 games. We've gained enough league points, and now it's time we're eligible to get promoted to the next tier. Sorry, the next division within the tier that we're in. Well, that's just a best 2 out of 3. So this is kind of like a chapter 2 problem almost. If we want to win the best 2 out of 3, the only way to do that is to either win and then win, cool, or win, lose, win, cool, or lose, win, win, also cool. Any of those possibilities, and there's no other way to win a best 2 out of 3. So to do that, we've assumed here again that your promotion matches are still the same probability of winning, which is 60%. So we have win, 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 lose, win, lose, win, win. We add those all together, we get 0.648. So even when you get up there, you've got your 100 league points, you don't necessarily get promoted. You might lose that promotion match, and then you sort of have to like wait a bit and like, then you can try again. So we can think about how long it would take to get promoted, which turns out to be 5.16. And that's actually a fairly complicated calculation, pretty annoyingly beyond the scope of this course. But if anyone super duper cares, you can ask me and I can write it out. Basically what we do is use an argument involving conditional random variables. So you've heard of conditional probability in chapter 4, and you've heard of random variables in chapter 5. There are something called conditional random variables, which are not covered in this course, so don't worry, you don't need to know them, but they're kind of neat, and they can be used to solve problems like this. So it might take, 2 games to get promoted, right? If you just win, done. It might take 3 if it's one of those other cases, the lose, win, or the win, lose, win. Or you might fail, and then you have to go back to the beginning and keep trying again. And so you can use conditioning to calculate the overall expected value of how many games it will take you to get all the way through and finish that promotion. So 5.16 games to do that. Okay. We do that a bunch of times. So we get, 38 or 39 games to get to 100 league points, about 5 games to get promoted. Then we're in bronze 4. And then we do the same thing to get to bronze 3, 2, 1. And then to get from bronze 1 to silver 5, it's now a best 3 out of 5 situation, which again, we can calculate using the techniques that we would have used in chapter 2, the probability of winning the first 3 in a row, or winning 2 out of the first 3, but there's 3 ways we could do that, right? We could be win, lose, win, 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 lose, or lose, win, win. So 3 times the probability of winning 2 out of the first 3 and then winning the 4th. Or we could win 2 out of the first 4, and there's 6, which is 4 choose 2 ways to do that, and win the 5th. So overall, that's another pretty good probability of winning. And then same thing, same kind of conditioning calculation to figure out it takes on average 7.71 games to get promoted. So with all of these assumptions, none of which are perfect, but all of which are pretty reasonable on average, to get from bronze 5 all the way up to diamond 1, we would need the following. First of all, we would need to get through each division. So 38.46 times 24 to get like from 5 to 4, 3, 2, 1, 5 to 4, 3, 2, 1, 4, 3, 2, 1, 4, 3, 2, 1. So 923 games to progress through each division. Okay, cool. Then to get promoted between the divisions within each tier, there's 19 times that you need to do that. That was 5.6 of those. So 98 games to get promoted on average. And then 31 games to get promoted between the tiers. So from bronze to silver, from silver to gold, gold to platinum, and platinum to diamond. Altogether, that is 1,052 games. And remember, that is just the average. The variance is huge around this number. So I just thought that was a neat application of mean of expected value, looking at how to progress through the leagues in this particular game. All right, if there are any questions, please let me know. Okay, right, someone asked on Piazza, what if you win? But you're right, you only need to win the 2 and then you move on. Exactly, yeah, so it is actually, yeah, thank you for mentioning that. Someone in the chat said this sounds a lot like a random walk. It very much is. So the random walk is a cool statistical model. Maybe I'm going to scroll down and talk about the random walk. So you're basically, you're on a number line, you start at the origin, and then on every step you flip a coin, and you either go up 1 or down 1. So if you get heads, then you go up to 1, 2, go up to 1, go down to 2, maybe you get a tail, then you go back down to 1, maybe you go back down to 0, maybe you go to -1, etc. And we can think about this number line. If the probability of going up and the probability of going down are the same, then like on average, we're going to stay at 0, like the average number of steps we're going to take. But of course, we could get arbitrarily far away from 0. And then once we're somewhere, like once we've gotten to 3 or whatever, then any future movement is centered around 3 because we got there. So the random walk is a neat, it's an example of a Markov chain, which is a cool model. I'll be talking more about that when we get to chapter 9, I think. But yeah, a random walk is exactly, this is kind of like that. And in this case, we have a probability of going up of slightly higher than 50%. So then on average, we're going to drift upwards in this process. And there's lots of variations of the random walk. You could think about a random walk where there's like 0 is like an absorbing state. So like if 0 is like the amount of money that you have, once you get to 0, you're stuck there because you're bankrupt. And then you could think about calculating the probability that you get to, if you start with $10 and you're going up by $1 every time you play a game, what's the probability you get to $20 before you get to 0, before you go bankrupt? So there's all sorts of interesting problems that you can answer with the random walk. And if that sounds interesting to you, then you should take Stat 333 or 334, because both of those classes talk about the random walk in a lot of detail. There's some really cool math involved. Thanks for mentioning that. All right, awesome. Okay, that was a really long, I'm sorry, that was like a 3-page long document. There's just so much to say about LOL, so I wanted to go into detail. The second thing I want to talk about is, just in general, there's not a lot of math today, but the idea of bias in data. So what I'm going to do is actually go over to Piazza for a second and have a look at my thought question that I posted at 1:23 this morning because I was still awake helping people finish their midterms. Okay, hey, we've got 39 votes so far. And the question I asked was, how many kids are in your family, including yourself? So 13 said 1. 16 said 2. 4, 5, and 1. So that's our sort of frequency chart there of like the number of kids in the family. And so we can then calculate, of course, the mean, the median, and the mode of that distribution. So the mean we know is going to be, well, I guess the total number of kids represented by all of these families, which is 13 times 1 plus 16 times 2 plus 4 times 3 plus 5 times 4 plus 1 times 5, all divided by 39, which is equal to 2.102 kids on average. And the average number of kids in a Canadian household, if you look at the census data, is around 1.8. So I just looked that up. The average family size, according to the census data, is about 1.8 in Canada. They're about to do another census, of course, like 2021 is another census year. So we'll get new data that I can use for next time. So the question is, why do we think that this number is different from this number? There could be lots and lots of reasons. And if you have any thoughts, actually, I'd welcome if you can post them in the chat or on Piazza. But why is that different? Obviously, it's possible that this is just a pretty small sample, right? 39 people is not a lot compared to the population of Canada. So maybe if we asked more people, we would get a number that's closer to 1.8. But I've done this every term that I've taught Stat 230 for the last 14 years, and it's always bigger. And I've surveyed like classrooms of 200 people, and it's always bigger, consistently bigger than 1.8. So I think at that point, I have enough sample data that we are seeing a systematic difference in the average family size among the Stat 230 students that I've asked this question of compared to the census data from the entire country. And there could be, again, tons of different reasons, but probably I think the most significant reason is that the sample that we take in class is not a representative sample of the population of Canada. If we think about like asking a random family how many kids they have, that's going to include families that have the kids are grown up, like you folks, but it's also going to include families that have one kid that's very young and they're planning to have more. And I would hazard a guess that it is unlikely, maybe not impossible, but unlikely that any of you folks are going to be getting a new sibling anytime soon. It's possible, of course, but it's much less likely. So we have a biased sample of people here. We have a sample of adults, adult kids, whatever, you're not kids, you're adults, but I'm talking about like your siblings, which is not representative of a randomly selected family within the country. So that, I think, is the biggest difference. But there's lots of other reasons that could be the case. One that comes up a lot is selection bias. So if you ask people, oh yes, there are also international students for sure. So if we have international students from countries where family sizes are systematically different, that might also be a contribution. So yeah, absolutely. That's if I'm comparing to the population of Canada, that's not necessarily a fair comparison either. Excellent point. Thank you. So definitely. Oh yeah, I think that was one of the things I thought of, but you thought of it too. Excellent. So different socioeconomic status as well too. Like if your parents are fortunate enough to be able to send you to university, that's really great. And then maybe that has an impact on the family size in one direction or another. The other thing I want to mention was this idea of selection bias. This is kind of interesting. So if you pick a random family and ask how many kids are in it and calculate that average, you will get a different average than if you pick a random person and ask how many siblings do you have. Think about that for a second. Like even if we were able to take a perfect sample where we were able to take an entire population and ask literally every single person, so there's no sampling bias at all. If we pick a family and ask how many kids are in it, we get a different average than if we pick a random person and ask how many siblings do you have. Think about why that is. It's kind of the same problem actually as measuring class size. So imagine like a university has a bunch of classes and like one of them is very small, like 5-person, and then one of them is like a 50-person, and one of them is a 500-person. Just this university only offers 3 classes. So there's a 5, there's a 50, and there's a 500. If you take the average class size, you take those 3 numbers and add them up and divide by 3, you'll get a particular average. But if you pick a random student and ask them how big the class they're in is, you're 10 times more likely to get one of the students in the 50-person class than in the 5-person class, and 100 times more likely to get a person in the 500 class than in the 5-person class. So when you ask people rather than families, or when you ask students rather than classes, the classes that are large are overrepresented in that sample. Isn't that neat? So weird. And it's kind of hard to see when the numbers are close, but that could be what's happening, right? If we pick a random person and ask them how many siblings they have, people with a lot of siblings are more likely to get picked because there are more of them. And then that'll bias the average upwards. So selection bias is another really interesting thing. There's other sources of bias as well that I didn't include on here, but things like sampling bias, which is maybe the people that respond to a survey are systematically different in some way. So if we're thinking about a survey, maybe people who feel really strongly about it will be more likely to fill it in. If you look at like reviews on Yelp or something, if you had a really bad experience at a restaurant, you're more likely to respond and give them a terrible review than if you had an okay experience. So that in terms of like who actually responds to surveys, there could be some sampling bias there. Or even just the method in which that sampling was done. Like if you're going to open a phone book, I don't even know if those exist anymore, but if you're going to call a bunch of landlines to do a political survey, you're going to get a different segment of the population than if you do an internet survey, for example. Very different in age, probably different in beliefs. Like you want to make sure that you're hitting the target demographic that you actually want. So there's lots of other sources of bias. Another one is like survivorship bias. Survivorship. And a really cool example of that is, so if you sort of, I can't remember which conflict it was, some war at some point, they were analyzing the bullet hole patterns on the undersides of the aircraft that came back and found that most of the aircraft that came back had bullet holes under the wings and under like the front and back, but not under the engine of the plane. And they were like, oh, okay, we better reinforce those areas that got those extra bullet holes. But in fact, that was the exact wrong thing to do because they were seeing the planes that made it back. If we think about the planes that didn't make it back, those were the ones that were hit in the engine. And so they realized, luckily, that the right thing to do was to reinforce the areas where there were fewer bullet holes in the planes that came back, because it meant that the ones that got hit there were the ones that didn't come back. So that can be really tricky sometimes, detecting survivorship bias or detecting sampling bias or selection bias or all of these other things. But the basic idea is, anytime you're working with any kind of machine learning algorithm, it's only going to be as good as the data. There's a good phrase, garbage in, garbage out. If you build a model based on garbage data, you're going to get garbage results. The data has to be reflective of the thing that you're trying to measure. So it wants to be representative of the population. If you're trying to model a population which includes international students, then survey those people as well. If you're trying to, if you're trying to get the political views of a population in a city and you only call landlines, you're not going to get a representative sample of the people that actually live in the city. So, and then the predictions of the model are going to reflect that biased data. So making sure that your data that you're using to build your models is accurate, appropriate for the purpose, and representative of the population it's trying to model, that is a huge, huge, huge important component of good machine learning practice. Alrighty, so that is all I wanted to say about this. Is the second part of the midterm being marked on Mobius? No, it's being marked on CrowdMark. So you will not see a mark through Mobius, and it won't come automatically to Learn. So again, if you did see a mark on Learn from part 2, it is not your mark. Your mark will be based on the work that you've done, and like you'll get tons of part marks for all of those other sections, and that'll be given to you through CrowdMark. So when the TAs have been given the solutions, they've already probably started marking, and we've asked for them to finish within a week, so we'll be able to give it back to you by next Friday. Thanks for the question. For computer-assisted assignment 1D, I noticed the answer was the same as calculating your post-test probability of infection and using that probability as a proportion of population with the disease. Why is this? That's a fabulous question. So that's not how we expected you to solve it. I expected you to solve it kind of the second way. So why don't I get out the solutions here? Yes. So again, this is 1D. Assuming the person tests negatively twice and those results are independent, what's the person, they're not independent, sorry, they're independent given the disease status, what's the probability the person actually has COVID? So the way that we expected you to do it is the second way, which is kind of the way that I gave the big hint for, which was if A1 and A2 are the events that the first and second test were positive respectively, then we want the probability of having COVID given that you have 2 negative tests. So this is what we're looking for here. And then by Bayes' rule, we can split that up into the probability of B times the probability of A complement intersect A2 complement given B, and then on the bottom, dividing it up using the law of total probability. And then we use independence of those test results, so we can split this up into these two things, and similarly for the denominator, and then we can calculate it, and we get 0.00203. But another way of doing it was basically treating those two tests as like one protocol and thinking about like defining a new P, a new probability P. Sorry, here. I'm going to just scroll down so I can actually point to everything. Okay. Sort of thinking, defining a new test as like two tests, basically. And then thinking about what's going to be the true negative rate and the true positive rate of that new testing protocol. So the probability that someone with COVID tests negative twice, that's going to be basically 1 minus the true positive rate of the individual test squared, right? So that would be like, given that they have COVID, the probability that they test negative once is 1 minus TPR. And the probability they do it twice, it's independent given that they have COVID. So that's going to be 1 minus TPR squared. So this is our new kind of like false positive, sorry. This would be a person with COVID tests negative twice and is deemed free of COVID. So that's basically saying that if you have it and the test says you don't, that's the false negative rate, right? So this whole thing is the false negative rate. We didn't define that, but it's 1 minus the true positive rate of the new test. So that's the probability that someone with the disease slips through this protocol. That's the false negative rate, or the 1 minus the true positive rate. So the new TPR is 1 minus, oops, sorry, I got a weird notification. There we go, sorry. 1 minus the old TPR squared. So 1 minus the old TPR squared. And then similarly, we want to find the true negative rate of this whole testing protocol. So in that case, we're thinking about a true negative rate means they don't have it and they are told that they don't have it. So the correct result. So the true negative rate, a true negative would be someone who does not have COVID tests negative twice, which means true negative rate for the first test times the true negative rate for the second test, because again, they are independent given that the person does not have COVID. So the probability that they are correctly identified as not having it is TNR squared. And again, that's basically like the new TNR of this new testing protocol is the old TNR squared. So with that in mind, this whole testing protocol now has a TPR and a TNR. Sorry, that should say TN. Yeah, it does say TNR of these two values. And then we can do the calculation that we did before in terms of finding the probability that they actually have COVID using the same formula as we did before, but just with subbing in these new values. So does that answer your question? I don't know if anyone thought of doing the question this way. I think probably most people did it the other way, which is what we expected, but this is kind of a neat way of thinking about it. You can have a really complex protocol, as complex as you like, but if you can find the true negative rate and the true positive rate of the entire protocol as a whole, then you can do these calculations. Another question, yes, could you go over 2A4 on the CAA? Also for 1D, I'm still confused why it was not. Okay, so I can answer I'm just going to answer the second part of your question first. They're not independent, right? They're not independent. They are independent given their disease status, which is very, very different. So independent given their disease status means if they have COVID, then the probability they test positive twice is the same as given they have COVID testing positive once times given they have COVID testing positive twice. And same thing if they're negative, and same thing if they don't have COVID. So if they test positive once, we know that they are more likely to have COVID than if they didn't. And so it makes it more likely that their second test would also be positive. So the tests themselves are not independent. They're definitely not independent because they have different probabilities of occurring given that the person was positive or negative. Was infected or not infected. So I think that's the key. You misinterpreted the question. It's not that they're independent. They're definitely not independent. You could prove with the information you've been given earlier on that they're not independent. But they're independent given the disease status. And then, so yes. Okay, cool. Awesome. And then, yes, I will go over 2A4 on this CAA. So what we need here, again, this expression looks like a mess. We want the largest number to be 4 times larger than the smallest number. So this is a pretty obscure thing, right? There's no formula for this. This isn't something we've seen before, but we can think about breaking it down into what we need to happen. If we want the largest number to be 4 times larger than the smallest number, that means we need a 4 and a 1, at least one 4 and at least one 1, and any of the other numbers have to be between 1 and 4. Right? Because if the smallest number, there's no other numbers between 1 and 6 where one is 4 times the other. If we had like a D20, then it would be a much more complicated question. But just to like note that at the side is that we need at least one 1, we need at least one 4, and we need all numbers between 1 and 4. So that's complicated, right? And the problem with at least one of something and at least one of something else is it can be really dangerous and it can be really easy to double count situations. Like if you just say, okay, let's make sure we have at least one 1, so put a 1 in there, and then at least one 4, so we'll put a 4 in there, and then the other two can be anywhere between 1, 2, 3, or 4, so let's do 4 squared and 4 squared, and then, okay, we got them, let's mix them up, so multiply by 4 factorial to scramble them up. That would be tempting, and if anyone did that, again, I forgive you because that's a sort of easy sounding solution. But the problem with that is if you got a 1 and then a 4, and then another 1 and then a 3, let's say, that event, 1, 4, 1, 3, is going to be counted multiple times because this one and this one could switch places. And it would be the same thing, but like which one you count as the one that was deliberately on purpose the 1 and happening to have a 1 amongst the other two like free digits, it could happen multiple ways. Or like same thing, if you got a 1 and you got a 4 and then you got 2 more 4s in the other numbers that were between 1 and 4. Well, there's like 6 ways that could happen, right? So it's tough to, especially when you have like repeated things or at least one of something, it can be tricky and you might want to think about breaking it up into cases instead. So let's do it that way. We basically want to think about it, breaking it up into cases. We can either have, we pick either 1 or 4, whatever, but we could have 1 4, 2 4s, or 3 4s. Those are the only possibilities, right? Can't have 4 4s because then we don't have a 1. And we can't have no 4s because we need a 4. So we'll just break it up into those 3 cases. And those are mutually exclusive, so we don't need to worry about any overlap. So then we have 3 cases that we're just going to add up those 3 cases. Done. Well, each one, we can think about it as how many 1s are occurring in that. So in the first case here, like if we have 1 4, then there's either 1 1, 2 1s, or 3 1s, right? Same thing, kind of like a sub case of the first one. Because again, like doing that at least one, the danger is double counting easily. So within the case where there's exactly 1 4, we can have either exactly 1 1. That makes it easy because then we just need to pick 2 other numbers, and then that either 2 or 3, and then mix them up however we like. If there's 2 other ones, then we just need to pick 1 other number and then mix them up. And if there's 3 other ones, then there's no other ways to choose the numbers. It's just about ordering. We have 4, 1 1 1, and then we could mix those up in 4 different ways, right? Like 4 1 1 1, 1 4 1 1, 1 1 4 1, or 1 1 1 4. So that gives us these 3 numbers here. In terms of, so like this is of 1 4 and 1 1. This is 4 and 2 1s, and this is a 4 and 3 1s. And then other, sorry, that's really hard to see. Hopefully that made sense. So that's how we get that first term there. So this here represents the case where there is exactly 1 4. But within that, there's 3 subcases. And then we're going to do the same thing for 2 4s, right? If there's 2 4s, then there can either be exactly 1 1 or 2 1s. And we can calculate those. And then the last case is where there is 3 4s. And the only other possibility at that point is the last one has to be a 1, because we need to have at least 1 1. And so there's only 4 ways for that to work, because it can either be, again, 4 4 4 1, 4 4 1 4, 4 1 4 4, or 1 4 4 4. So that, doing it this way is like a little more time consuming, but you got to be really careful never to like double count things, never to overlap. And when you do it this way, when you split it up by basically like exactly this number of 4s and exactly this number of 1s, you know you're not going to run into the danger of double counting anything, because you've specified exactly how many of each number there are. Does that help for 2A part 4? That was definitely the trickiest part on the assignment. That was the kind of wild card one. Yes, yeah, exactly. Simple sounding question, but tricky to calculate. Sometimes it's deceptive. Sometimes hard sounding questions end up being easy, and sometimes easy sounding questions end up being hard, and sometimes they're the way they sound as well. Great. Oh, question as well. Not sure if someone asked already, but when will we be able to view our marks for part 1? Great question. We still have not 100% decided. There are still a couple of people writing that had technology issues, so we're not going to release it just yet. I did mention that the TAs are marking part 2, and that will be done within a week. So we may just release all of it at once, just for simplicity, so you know your whole midterm mark at a time. I will talk to the other instructors if there's a huge desire to release part 1 marks first, and then get the other half of it later. I don't know what the advantage of that would be, but if you have a compelling reason, you're welcome to email me. But certainly, absolutely within a week for sure, because that's when part 2 will be done, and we'll certainly release both of those at the same time, if not part 1 earlier. Thanks for the question. Thank you very much for all of those great questions, and thanks for tuning in. I will see you next week, and good luck on everything else you have going on. Have an awesome day. Bye.